Hello students, today we are learning calorimetry experiment. So this is the wooden box which is in your textbook shown in the figure 11.1 calorimeter. Okay, now I am going to explain what are these experimental setup requirement for this. So here is the wooden box. This is the insulation to protect the heat or to maintain the temperature inside this wooden box. Okay, so this is important. This is also named as heat loss sheet. Okay, this is we are using as an insulation. Then this is a stirrer. We are for stirring we are using this. Then this is a stand for holding a thermometer. This is a thermometer and this is our copper vessel. Okay, we know, see, this is a good conductor of heat. Okay, so the vessel soon acquires the temperature of its content. Okay, we are pouring a hot water in this container, copper vessel. We are going to add a hot water in this vessel. Okay, also this copper has a low specific heat capacity. This copper has low specific heat capacity. So the amount of heat energy taken by the calorimeter itself from this hot water to acquire its temperature is very small. Okay. Then the outer and inner surface of the vessel. This outer and inner surface of the vessel are cleaned. Okay. And here, to reduce the loss of heat due to radiation, this is polished. For insulation inside the jacket, inside this wooden jacket, the space will be filled by this insulator. Okay, this is how the experimental setup inside this. Okay, then the space between the calorimeter and the jacket will be filled with some poor conductor, and the jacket this is a poor conductor of a heat. Okay, why we are providing this? For to avoid the heat loss by conduction, conduction. Now I am keeping this inside this wooden box. Okay, so now I am keeping this inside. Okay, now what next is, see, this is the experimental setup. Understood? Then I am going to pour a hot water inside this. I am adding hot water in this jar. See, now I am placing a lid on this. This is a wooden lid. Why to place it? See, you can see these fumes are coming. So to protect this from a convection loss. Okay, so I am placing it inside this. Okay, done. Before that, I have to place this stirrer in this. Okay. Okay, so this is a stirrer, and now I am placing inside this is our thermometer. So once we place this thermometer inside this, okay, the temperature starts rising. Initially this thermometer was showing room temperature, and now you can see here, initially the temperature was shown by this thermometer was room temperature, which was 16 degrees Celsius, and now you can see this is around 76 degree Celsius. You can see this. Okay, so mercury is above 75 degrees Celsius. Here it is. Okay, so this is the reading which you can take. Okay, so here you can observe that here one hole is given for this keeping this thermometer. This is for stirring, This is for stirring this one liquid inside this calorimeter. Okay, and now the temperature. Can you see it is about to 75 degree Celsius. Okay, so this is the temperature recorded by this thermometer. Okay, now when I am explaining now what when a hot body is mixed, it means hot water is mixed, or I poured it in the this container. Okay, so which was cold body. Okay, so heat energy passes from this hot water to this cold copper vessel. Okay, so here what happened, till both the bodies attains the same temperature, then we are using copper here, so what happened, it attain the same temperature quickly. Okay, see here, before the temperature shown was 76, then 75, and now here the temperature is shown in this is about 73 degrees Celsius. So it is decreasing slowly. Slowly it is decreasing, because here air is passing from this part. But no matter, we had taken care of all the heat, protecting it from all the heat losses. Okay. Okay. So in the previously only I showed you that we put a insulation, we put this wooden block. Okay, we cover from the convection losses are covered by this wooden lid. Okay, so all these three losses we try to minimize. Okay, but then it goes on decreasing, but the rate of decreasing is slower. If I keep this vessel openly here, no, this cooling rate will be faster, as the temperature difference, heat transfer to the surrounding medium, as there is no any protecting things are there. So there the heat transfer or cooling rate will be faster, whereas it is slower. Okay. So if no heat energy is lost to the surrounding, then it is a perfectly insulated, right? If no heat loss takes place in this, then it is a perfectly insulated. Then the formula will heat energy lost by the hot body is equal to heat energy gained by the cold body. Okay, so heat loss is equal to heat gain. Okay. Now in this mathematical statement for the calorimetry, let A be the mass M1. Then specific heat capacity C1 at a higher temperature. T1 is the higher temperature. B mixed with the another substance B of mass M2, specific heat capacity C2 at a lower temperature T2. Now here A is here this substance A is our water, okay, of mass M1. It is approximately 50 ml mass. Okay, specific heat of this water is a C1, okay, which is at a higher temperature. Okay, hot water we pour in this vessel, right? Then substance B is a copper vessel, its mass is M2. Now specific heat capacity for this copper vessel, means for copper it is C2, and at a lower temperature, it was a cold, so the temperature is T2. So this substance B is a copper vessel which is at a lower temperature, okay, which is at a lower temperature. So T2 is less than T1. T2 is a copper vessel and T1 is a hot water. So copper vessel temperature is less than hot water. Understood?
Yes.
If the final temperature of the mixture after heat exchange becomes T, okay, when I pour this hot water in the vessel, Then the fall in the temperature of the substance A means what? Water. It will be T1 minus T. Then rise in the temperature of this copper vessel which is T minus T2. Okay. Heat energy lost by A because A is at a hot temperature. So what is the heat energy lost? M1 C1 into fall in the temperature means what? M C delta T, right? That formula we learned, M C delta T. Now this M1 for water, C1 for water, and temperature fall in the temperature is delta T. So we are replacing this delta T by T1 minus T. So M1 C1 T1 minus T. This is for a heat energy loss by water. Now, we know this copper vessel was at a room temperature. So, when I pour this hot water in this copper vessel, then heat energy gained by this vessel is by B. Okay. So, now we put these values in the formula. Mass for the copper vessel, specific heat C2 for a copper vessel into rise in a temperature. So it is M2C2 in bracket T minus T2. So if no heat energy is lost to the surrounding. Okay, we know that no heat energy loss takes place. Because of all this construction, we covered all the heat loss by conduction, by convection, by radiation, all these three heat loss we minimized. Okay. So, if no heat energy is lost to the surrounding, then by the principle of main method of mixture, heat energy lost by A is equal to heat energy gained by B. So heat energy lost by A means water is equal to heat energy gained by copper vessel, that can be formulated as M1C1 in bracket T1 minus T is equal to M2C2 in bracket T minus T2. Okay. So this is what? Energy lost. Heat energy lost by A is equal to heat energy gained by B. This is experimentally proved our calorimetry experiment. Okay. Thank you so much.